Okay, welcome back. This is 5.6. We'll talk about defining sequences. What is it? Defining sequences recursively. Ultimately, we'll want to find closed forms for these recursive sequences. The Tower of Hanoi is in this section, if you've ever heard of that, and the Fibonacci sequence. Okay, so let's get started here without further ado. 5.6. We've already played around with these a little bit. Okay. Let's look at some recurrence relations. We dealt with some simple ones. So later we'll classify different kinds of recurrence relations in the same way that, and you probably haven't done it yet, but if you took like differential equations, it's just like that. It's almost the exact same thing when you're dealing with kind of like the linear differential equations, and you can kind of factor them to get the characteristic equation. It is exactly the same. It is mind-blowing. But anyways, we'll list, all we want to do here in the beginning is list some terms of a given a given recursive formula. So for instance, b sub k equals b sub k minus 1 plus 3k for all integers k greater than or equal to 2. Okay. For these kind of problems, you need some some initial conditions. Okay. So b1 is listed as 1, and then b2 is I guess we just need b1. Okay. Okay. So once you get b1, what you're going to do is put it into the formula here. Okay. So right here. So b2 is equal to b sub 1, which is 1, plus 3 times k, which in this case is 2. Okay. So it's 1 plus 6, which is 7. Right? So once you get b sub 1, then b sub 2 is equal to b sub 2 minus 1 plus 3 times 2. So wherever you see k, you're just putting in the index. And then simplifying it, it would be b sub 1 plus 6. And of course, b sub 1 is the initial value that's given in the book. That's just 1. Okay. And then you can continue this way. B sub 3 is the previous one, which is 7, plus 3 times the k value there, which is 9. So that would be 16. And finally, b sub 4 is 16 plus 3 times the k value, which is 4, so 12, 28, right? Okay, let's try another. I got number 6. T sub k equals t sub k minus 2 plus 2 t sub, whoops, this would be k, the first one's k minus 1. Minus 1. The second one is what is it? K minus 2. And this one they want for all integers k greater than or equal to 2. And so we'll need two initial conditions for this type. T sub 0 is negative 1, and then t sub 1 is 2. Okay. You can get general sort of sequences built off these things if you don't give the initial conditions, and we kind of deal with that a little bit later. And then you have to solve for the basically the coefficients of your I guess your solution to the recurrence relation. But anyways, let's get ahead of myself. T sub k, right? So t sub 2 is going to be the previous term, t sub 1, 2, plus 2 times the previous term. Okay, the k minus 2 term, which in this case is t sub 0. So I have negative 1. 2 minus 2 will just be 0. T sub 3 is going to be the previous guy plus 2 times the previous guy, So that would be 0 plus 4, which is 4. One more. T sub 4 is the previous guy plus 2 times the previous guy. So that'll be 4 as well. Okay. So what we're ultimately going to be looking for are kind of the closed form solutions of these recurrence relations. And we want to show first that a particular closed form solution satisfies the recurrence relation. And it's, again, if you took differential equations, it's just like showing a function as a solution to a differential equation. Even more simply, though, it's very similar to showing a solution satisfies an equation. So everybody is familiar with something like this. 3x plus 1 equals 4. Check to see that x equals 1 is a solution to that equation, right? So you have left-hand side, right-hand side, plug in 1, so 3 times 1 plus 1. 3 times 1 is 3, plus 1 is 4. Okay, on the right-hand side it's 4. The right-hand side and left-hand side are the same, so therefore it is a solution. Okay, that's the kind of same thing we want to do here. We'll start on one side and move to the other side. And it's a little different in that instead of having a number that satisfies an equation, we'll have an equation which satisfies another equation. It's just there will be two types of equations where one's a recursion equation. Okay, okie dokie. So hope that makes some sense. Let's take a look. So satisfying recurrence relations. Okay, so number 9, they give you kind of the solution equation, and they're going to call that the explicit formula, which from before is basically our closed form formula. Okay, so the explicit formula is going to be a sub n equals 3n plus 1 for n greater than or equal to 0. The recursion formula, which is kind of what you would be given, like you would tackle the problem you're dealing with and assign a recursion formula to it, like with the Tower of Hanoi that we'll be looking at here soon. So we'll show it satisfies some recursion, and the recursion that's here is a sub k equals a sub k minus 1 plus 3 for all integers k greater than or equal to 1, and they give you your starting place a sub 0 is equal to 1. Okay, so ultimately they'll give you this thing I'm putting in a box right here, and then they're going to want you to figure out this answer here. Okay, and it's just like what we kind of did back here in algebra land, you know. What eventually happens is they give you this equation and want you to figure out this, right? And that's easy. We teach you tools for doing that. You just subtract 1 from both sides and then divide by 3. Oh, I got the answer, right? Oh, that's magic. No, okay. All right. So somehow there's some way that we'll be able to build these explicit formulas, and we'll do that in like 5, 8. Okay. So anyways, for the meantime, we want to show that this explicit formula is kind of a solution to the recursive formula. So first, yeah, let's talk about again the difference between the recursion and this explicit. Okay, so the recursion formula versus the explicit. And why would I want an explicit formula? It's because the explicit formula is kind of independent of previous values, whereas in a recursion you need to know the value before it to get the next value. So a sub 0 is 1, a sub 1 is the previous 1 plus 3, so that's 4, a sub 2 is the previous 1 plus 3, so that's 7, etc. Right? So this will be plus 3 is 10, a sub 4 is 13, a sub 5 is plus 3 is 16, sorry. Yeah, so but the explicit formula is independent of that. I can just say, hey, what's a sub 4, and plug it into the formula, the 3n plus 1 thing. You get 3 times 4 plus 1 is 13, right? So that's the advantage, and again, that's the difference. I may have talked about that in the previous video, but there it is. Okay, so I want to show that the explicit guy satisfies the recursion formula. It's like saying it's a solution to the recursion formula. Okay, so what I'm going to do is start on the right hand side of the recurrence relation and use and substitute in the explicit formula. So starting, and I'm not going to make this too formal. I'm not going to do it like my direct proofs, but starting on the what do we want to start on? The left hand side? No, the right hand side. I'm going to start on the right hand side of the recursion. I have so looking back, a sub k minus 1 plus 3. Okay, so I have a sub k minus 1 plus 3. Right, now I'm going to do a substitution with the explicit formula. So you know, in my brain, my explicit formula was given above as a sub n equals 3n plus 1, right? So to do a substitution here, I'm just replacing n here with k minus 1. So this new formula after the substitution, if I can get my pen to work, there we go, is going to be 3 times k minus 1 plus 1. Okay, so maybe my writing there is a bit misleading. 3n plus 1. Okay, a sub n is 3n plus 1. And I just plugged in k minus 1 for n. Okay, then I go ahead and distribute 3k minus 3 plus 1. And I'm hoping to land on the right hand side of the recursion relation, which is a sub k. Right? Okay, so this is then 3k, oh, that's a 3 right here. 3k minus 3 plus 3 plus 1. Sorry, so I lost my plus 1 here. Okay, I see what I did. Okay, let me erase. Sorry, this is just turning into a mess. I'll make this more clear. Okay, so again, my formula for a sub n is 3n plus 1. So I want to figure out what is a sub k minus 1. And I'm saying that's literally just replacing n with k minus 1 like that. Okay, so I'm replacing this thing with this thing, and I get 3 times k minus 1 plus 1. But last time I wrote it, I forgot the plus 3, right? So I still need the plus 3 in there. And then we can simplify that to be 3k minus 3 plus 1 plus 3. Okay. And then that will equal 3k plus 1. And again, if you look back to our explicit formula, that thing is just a sub k, which is what we were trying to show. So we've essentially connected it now to the other side and shown that the explicit formula fulfills a recursive relation. Okay, it's a little weird, but it's really no big deal. Okay, so hence, once you get a little bit more experience under your belt with other kinds of classes in mathematics, this is no big deal. So anyways, hence the explicit formula kind of is a solution, or it works. Okay, great. Right. So anyways, let's move on to the Tower of Hanoi now. So what we're going to be doing is trying to find recursive formulas, and then in the next sections we'll try to find the explicit formulas for the recursive formulas, and then we'll prove the explicit formulas inductively, and then we'll give you some more high-powered techniques for finding explicit formulas. Okay, so anyways, we'll start with the Tower of Hanoi, and this was first marketed to children as a game, and I don't know, it's in the book, but you've probably seen it as a child's toy. So you have kind of a piece of wood with some poles sticking out of it, and then on the poles there's little donuts, okay, attached to it. So I'll draw my donuts like this. Anyways, the objective is to move all the donuts on one pole to another pole where you have some restrictions, and the restriction is you can't put a big donut on top of a smaller donut. Okay, so a bad move, for instance, let's say I'm first going to move the little donut to another pole, so I'll move it over here. And you want to get all the donuts on another pole, but you have to have them arranged in the same way, so they still have to have that Christmas tree kind of arrangement to them. So anyways, you can move that guy over to there, but then what you can't do is move that second donut onto the first little donut. Okay, so you can't go on your next move and say something like this. Okay, so that's a bad move. Okay, so again, the objective is to start with your tower, like right here, and then we want to move all of the objects in the tower one by one, so we end up on a different pole. Okay, so maybe there's other versions of this, and you'll see one in my WebAssign, or WebAssign, whatever it's called, where you're moving two disks at once, and it's basically the same thing except you just double everything. But generally what you want to do is end up on this third pole, but I don't even think that matters. You just want to end up on a different pole where they're stacked in the same way. Okay, our objective is to find a recursive formula to tell us how many moves it takes to get from the first yellow box to the second yellow box. Okay, and we'll first start by defining this m sub n, or if you want m sub k or whatever. And m sub k will be the minimum number of moves to move an entire tower of height k from one pole to the next. Okay, so this is the min number of moves to move a tower with k donuts from one pole to another. Okay, and the best way to attack this problem is just to play around with it a little bit. Pretend. Finally, I get to pretend I'm a little kid again, right? So we'll start with k equal to 1. Right? So this will be I don't know where to put it, k equals 1 sort of version. And we have our 3 poles, and we have one donut on it. Okay, so to get from one pole to the other, it just takes one move. Okay, there it is. So m sub 1 is 1. Okay, let's try k is 2. Okay, so now we have 2 donuts on the first pole. Okay, and what do I do? Well, I'm going to start the same way as before. So I'm going to move the little donut. And just so I can end on the third pole, I'm going to move the little donut right here. Okay. And then I'm going to move the big donut to the third pole. And again, you don't have to do it that way. So here's my little donut, and the big donut goes to the third pole. And then finally, I can move little donut on top of the bigger donut, and I am done. Okay. So in that case, m sub 2 equals 3, right? 3 moves. And what you're doing is kind of looking for patterns. Okay? You're iterating to find a pattern. K sub 3. So now I have 3 donuts. Okay. And the first task is really, and this is where we can see the pattern. I don't want to do hundreds of these, right, until we see the pattern. So the first objective is literally to just move the top part, which is m sub 2, over to another pole. Okay, and we have to do it where where you can't stack the big on top of the small, so it has to be done in the same exact way as before. And the way we would do that is the same way we would do m sub 2 above. Okay, so first I have to move m sub 2, and we could show that takes 3 moves. Okay. So again, here I am. Got my poles. The big pole is here. I have the big donut, and then I'm moving the small donut, and I'll move the small donut right here. Okay. And then my next move, I'll move the next size donut next door here. Okay, so the small one's there. And then I'll move, sorry, we're smushing this together. I'll move the littler donut on top of the medium donut, right? And again, that's just these moves right here. That's exactly just m sub 2. Okay, these 3 moves here is just m sub 2. Okay, then I'm going to I have to move that big disk, right? I move the big disk to the third pole. Maybe not be this one. So he's way over here. The smaller disks are still sitting on that pole. And then what do? Well, you have to move those 2 disks again. So you're going to essentially just repeat m sub 2 to get those 2 smaller disks onto the big disk. Right? So first I'm going to move the little one over here. And then I'm going to move the middle size one on top of the big one. And then I'm going to move the small one on top of these 2 here. And like I said, what's happening is m2 again. Okay. And then you could look at k equals 4, and you're going to see the same kind of pattern developing. Okay, so let's see what we have here. So this is m2 again. We're looking for what is m sub 3. So m sub 3 is going to be, well, m2 plus m2. There's 2 of those, plus there's 1 extra for when you move the bottommost donut. Okay, so what is that? It's 2m sub 2 plus 1, and of course that's just going to be, if you substitute in 3 for m sub 2, you'll get 6 plus 1, which is 7. Okay, so let's pretend we experimented a lot with that, and let's just move on now to some k equals n, right? Okay, so how is that going to work? And I claim we've kind of outlined it, right? So the first thing you're going to do is move everything except the bottom big disk to another pole, right? So here we are in the beginning. I don't know how tall it is, just put some extra dots in there. So the first set of moves will be moving all of this top stuff to another pole. Okay, okay, so here we go. I move all that. I leave the bottom one there, and then I move all of the other guys over here. You know, and how many moves does that take? Well, that takes your m sub n minus 1 moves, the number of moves it took to move a tower that's one step lower, or one donut less than the previous. Okay, so one donut less than the current. Sorry. So this is really just m sub n minus 1 moves. Okay. And then you're going to move the big donut over. Okay, so the big donut gets moved to there, and we leave this guy alone. Then finally, we have to take all of that junk and this tower and move it on top of this tower. Okay, okay, so we're moving, first move this guy over to here, and now we're going to move all of it onto the big donut. Okay, and again, you know, how many moves does that take? Well, it takes a number of moves to move a tower that has one donut less, which is m sub n minus 1 again. Okay, so we end up here. Sorry, all my donuts aren't the same, or they're supposed to be decreasing in size. Okay, sorry. Okay, so again, this takes m sub n minus 1 moves. Okay, and so finally, how many moves does it take for a tower of n donuts? Well, there's 2 sets of m sub n minus 1 moves, plus moving that one big disk on the bottom. Okay, and there's your recursive formula for the Tower of Hanoi. Okay, the next one is the Fibonacci sequence. They have a whole periodical dedicated, at least they used to. It's going, gosh, 20 years goes by so fast. 20 years ago, they had a Fibonacci book, a periodical that you could subscribe to, and it was all Fibonacci stuff. Every month you get a new book on Fibonacci. Anyways, our sequence, we'll think of it in terms of rabbits. So you're going to begin with a single pair of rabbits. Who were just born. Then the single pair grows up. Okay, so during the first month or whatever time period you're working with, the single pair reaches maturity and are fertile. Okay, and at the end of that sort of second month, they give birth to a single pair of rabbits. Okay, and then fourthly, no rabbits die. Okay, so let's take a look. And the way, so we're starting with our initial value is just one pair. Okay, and we're not going to write 2 for 2 rabbits. We're just going to write 1 for 1 pair. Okay, so we're going to call the first f sub 0 and call that 1. Okay. Okay, and then to suggest that they're not fertile, I'm going to put a circle around them. Okay. Okay, and then after that first year, they become fertile, so I'm going to get rid of the circle. Okay, and at the end of that time period, a month or whatever, they're going to reproduce. Okay, so at F2, you'll still have that pair alive, but then they're going to give birth to this other pair, which are not fertile. Okay. F sub 3, you're going to have the original pair. The newly born pair is going to become fertile, and the original pair are going to give birth to a new pair. f sub 4. These three guys are still there. The new one here becomes fertile. Okay, and then the first two here are going to give birth to two more, which are not fertile. Okay, f sub 5. What happens here? So I will still have all these guys plus the ones that could give birth. All right, so there would be 3 extra. And what's happening here is from 2 times before. So if I want to know how to get the number of rabbits for f5, what I do, and I should have circled the fertile ones. Sorry. So there's all of these guys plus these 3 new non-fertile. Okay, so to figure out f sub 5, what's happening? The 3 from 2 before are going to be able to give birth to these 3 here, and then you're still going to be left with the f sub 4 set, which will give you these guys here. Okay, so what's happening is that f sub 5 is basically f sub 4 plus f sub 3, and it turns out that's the pattern. Okay, so in general what we have is f sub k equals f sub k minus 1 plus f sub k minus 2. Okay. We want to do one proof for math people. This may affect their lives. So number 44. And then in the book they're going to give you a recursive definition of the sum and product, which is really just peeling off the last term of a sum or product. So to the side here, the recursive definition of a sum, I equals 1 to n, means to just rewrite it as I sub 1 to n minus 1, a sub I plus a sub n. Okay, so that's the recursive definition for sums. Okay, I wanted to use that definition in order to prove the triangle inequality for arbitrary sums. Okay, so note, for all reals, we'll assume the triangle inequality holds. And to prove this, you would have to do like a case-by-case analysis. You know, what if A is less than 0? What if B is greater than 0? What if A is less than 0 and B is less than 0? What if A is greater than 0, B is less than 0? And all the different variations, and you go through one by one and use the definition of inequalities to show that this holds. It's something like that. It's not something you would think up intuitively. It's just long and tedious. Okay, but everybody who wants to call themselves a math person has to go through it at least once in their life. So anyways, this thing's called the triangle inequality. And why is it important? It has to do with measurement and distances and rates of change, which is important to any, not just math, but any sort of science, really. You have to work with rates of change. And in order to work with rates of change, you need to have distances. And distances can be abstracted. Okay, so you can have not just the distance from point A to point B in 3 dimensions, but you can have these weird other kind of distance definitions. So the distance between x and y is equal to 0 if x is equal to y, and 1 if x is not equal to y. So that would be an example of a different kind of distance measurement. Okay, that would become the discrete metric. So we can abstract this idea of distance, but in order for it to really qualify as a distance formula, it has to satisfy a bunch of kind of facts, and one of the facts is this triangle inequality. So you can do these different abstract forms for distances and apply them to whatever science you're dealing with, And yeah, but it has to satisfy some things like the triangle inequality. Okay, so we want to use induction and the triangle inequality to prove that, but for arbitrary sums. So a sub 1 plus a sub 2 plus dot 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 plus a sub n is less than or equal to a sub 1 plus a sub 2 plus dot 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 plus a sub n, which if you write in summation notation looks like this. The sum from I equals 1 to n of a sub I is less than or equal to the sum of the absolute value of a sub I from I equals 1 to n. Okay? Okay, so we're going to do this by induction. And right, so and we want to show that this holds for n greater than or equal to 1. Okay, for integers n greater than or equal to 1. Okay, show proof by induction. How is this going to work? So first, the basis step. P of 1 is this thing, the sum from I equals 1 to 1 of a sub I, absolute value of, is less than or equal to the sum of the absolute value of a sub I from I equals 1 to 1. Okay. The right hand side is the sum from I equals 1 to 1 of a sub I, which will just equal absolute value of a sub 1. The left hand side is let's get rid of that, is the sum of the absolute value of a sub I from 1 to 1, which is again, it's just a sub 1, hence the inequality holds. They are equal in this case, which is the same as, which makes less than or equal to a true statement. So hence P of 1 is true, or it works, or some variation on that theme. Secondly, then we want to do the inductive part. So suppose k is a payback int such that k is greater than or equal to 1, and the sum from I equals 1 to k of the absolute value of a sub I is less than or equal, whoops, sorry, got it reversed. Of this is less than or equal to the sum of the absolute value of a sub I from I equals 1 to k. Right, it's just that. We want to show that the absolute value of the sum from I equals 1 to k plus 1 of a sub I is less than or equal to the sum I equals 1 to k plus 1, the absolute value of a sub I. Okay. It's long and tedious. This is why some of those professors will just say, well, it's clear that the answer is this, because they're sick of writing it out. That's what I suspect. It gets boring after a while, especially you do it like 5 times. It's like, oh, this. Okay, so anyways, we want to show that that's true. We'll start on the left. So note the absolute value of the sum from I equals 1 to k plus 1 of a sub I. We can use the recursive definition of a sum that I just introduced above to rewrite this as the inside of the absolute value as the sum from I equals 1 to k of a sub I plus a sub k plus 1, all in absolute values. And then we could apply the triangle inequality where we think of this as our A, and we think of this as our B. Okay. So our triangle inequality from above said that if you have a absolute value of a plus b, that's less than or equal to the absolute value of a plus the absolute value of b. Right? So we just use that fact, and now we can rewrite this is less than or equal to the absolute value of the sum from I equals 1 to k of a sub I plus the absolute value of a sub k plus 1. All right. Then we can use our inductive hypothesis, which, where is it? Back here, to replace this blue thing with this other blue thing, right? So I could say that what we have right now will be less than or equal to, let me get the other color going, the sum of a sub I from I equals 1 to k, absolute value of a sub I, plus the absolute value of a sub k plus 1. And then the reverse recursive definition for summations, we can grab this chap and plop them back into here, and that's kind of what we want to show. So I equals 1 now to k plus 1 of a sub I is our final place where we want to end up, and that's what we want to show, which is what we wanted to show. And they all rejoiced, right? Okay, and that's about it for this section, so we'll see you next time, and have a good day.